And to start, we'll draw a three-dimensional system. And let's say that on the xy plane we have a lamina. A lamina, if you don't know what that is just a very, very flat object. Very thin. So thin that the thickness is very negligible.
It's like those thin rods in physics.
Mm-hmm.
That actually have a thickness.
Yes. Okay. And now, again, we're going to inspect a piece of the lamina. So let's look at a little section of it. And at this point, let's say that that's x comma y. And first we'll say, well, what would the density be here? So we're going to call the density function delta of xy.
We called it rho.
It could be called a lot of different things. So typically we know that density is what? Mass over volume. Now, since this is a lamina and its thickness is negligible,
Mass over area.
we're going to say mass over area instead. Okay? So basically what we're going to do is this. The density of the lamina will be mass per unit area. Again, because we have very little thickness here. So then, if I write that out, what we want to do is take the limit as this area approaches 0. So then we'll have change in mass, change in area. And if we manipulate this a little bit, we're going to get delta M. So as we approach 0, it's going to equal density times delta area. And again, as these dimensions tend to 0, this delta M becomes just mass. dA is what we get from delta A. So now we have the double integral and that is our first application. It's not a horrible one. It's pretty straightforward. So this is really going to be your region R, and it will have some density function given to you, okay, where the density changes depending on what point you're at. Okay, so it's not uniform density per se. In physics, you can do the same kind of thing. I think. Have you guys talked about electric charge yet or anything?
We've done center of mass, or like eyes and stuff like this stuff with like integrals.
Okay.
It wasn't double integrals. We wrote like dm over dx equals the density function. We solved for dm and plug that into an integral where the teacher said that it was like 1 over m integral of r or something.
We're gonna get to that. Yeah, we'll get to that. Yeah, they always have different notation in physics. It's kind of funny. But hopefully this makes sense. Okay. Now, you know what? We can skip that example and just do one comprehensive one. Let's talk about center of gravity since we brought it up. Or center of mass, same thing. Did you guys talk about moments then, or no?
Yeah.
Okay. What's the moment?
It's like the sum of mr squared. That's like the grammar formula.
Mr squareds. Are you thinking moment of inertia?
Yeah.
Okay, not the same thing.
Oh, that's not what you mean by moment?
I literally mean just moment. It's like a static moment. Um, so let's define it. So let's just look at the xy plane. Let's look at one point, and let's call this point x sub k star, y sub k star. A moment is just the product of mass and distance from an axis. What might be the axis of rotation. Now, it can be any given axis, and for us, we're going to use the x-axis and the y-axis. So, well, actually, we can do any. Let's do any case. So let's say here we have x equals a. So let's say this is our axis, and we're looking at this point. Then we would say that the moment, which we're going to call m, about the axis x equals a is going to be mass times distance from the axis. So if this is x equals a, and here we have x sub k star minus a.
Are those m's and d the same?
No, this is mass, this is moment. Now, we can apply the same thing if we go about a different line, say y equals a. And then we would have mass times distance from this point to the axis, which would be the order's not going to matter. Let's just write it this way. But actually, no, let's not. Let's keep it the same way it should be. So if we do a minus y sub k star, that would be the general for this line. Again, depends where the line is. Okay, so that's the general definition for moments. Now, we're not going to really do much with this except lead us to the center of mass definition. Okay? Now, in order to discuss center of mass, we want to talk about the moment about the x-axis and about the y-axis. Okay? Now, if we go x-axis, using this kind of interpretation here, I guess we can stick with this. That would be mass times the distance to the x-axis, right? Well, what is mass, though? Whatever we defined up here. So let's just write that out. I'm going to leave a little space in the beginning because we're going to fill that in. So this is mass. All we need now is the distance to the x-axis, right? So we don't have to redraw a picture. How far would this point be to the x-axis? Or more generally now, without the star notation. This point to the x-axis would just be the y-coordinate, right?
Why do you put that inside the integral?
Well,
Because I think you're doing mass times this.
okay, so if you want to see it, mass was approximately the density function evaluated at the point, right? Delta A sub k. So then the moment is going to be approximately delta x sub k star, y sub k star, delta a sub k, and now multiply that with y sub k star. So then when we translate it, that's what we get for moment. Okay, so this, let me rewrite that, would be the notation for the moment about the x-axis. Similarly, the moment about the y-axis would be the same double integral. The only difference is instead of y times the density function, it would be x times the density function. Okay. So now, for center of mass, we want an x coordinate and a y coordinate. I'll call it x bar and y bar, such that mass times x bar will be the moment about the y-axis, and mass times y bar would be the moment about the x-axis. So that no matter if I took mass times this distance or if I looked at the moment about the y-axis versus the other one, the center of mass would make these two the same. Okay, so this is where the lamina would balance perfectly. So now, if I'm looking for x bar and y bar, and these conditions have to hold, now we have a relationship that we could use to say that to find the x-coordinate of the center of mass, the x-coordinate would just be 1 over m times moment about the y-axis, right? So 1 over mass. And then the moment about the y-axis is what we did earlier.
Oh.
Does this look more familiar now?
Yeah.
You didn't derive it, did you?
Was it say lambda would what?
Balance perfectly.
I think we did some sort of
Probably a little loose-ended. Not as, I don't want to say strong, but probably not as thorough.
We didn't take double integrals.
Okay. So here's the center of mass. So basically, here's what you need to know so far. This is how you find the center of mass, and how do you find mass?
Just the integral.
Of the density function, right? Okay. Don't worry so much about the derivations, but now you kind of know where these formulas come from and what they mean and what they do for us. Okay, so we'll do one comprehensive example here where we go ahead and find center of mass, center of gravity, and then also obviously we're going to have to find the mass to do that. So rather than say here's an example where we find the mass and do a different one, we'll just do one where we have to find everything.
Are we not going to find moment of inertia?
No. Yeah, that's what you were talking about, the sum of mass r squared, right?
Oh yeah. That was like the second thing we did with the integral. But we never actually had to do it.
Okay. So we got these formulas ready to go. So here's an example. Find mass and center of gravity. For the triangular lamina with vertices at 0, 0, 1, 0, and 0, 2. With density function 1 plus 3x plus y. Okay, so again, I'm a fan of sketching whatever you're working with. They gave you a region 0, 0, 1, 0, 0, 2. So here's our region. Pretty much easy to work with. The only thing we have to figure out is the equation of this line on the right, which is what? 2 minus 2x. Good. And now let's just find the mass. Because in order to find the center of mass, we need to find the mass. You know, to make our notation clearer, I think I used a capital M when I defined mass earlier, didn't I? Why don't you change that to a lowercase m? I noticed I stopped doing that. So when we first defined mass, I think I just wrote a capital M.
But then you wrote a capital M for a moment.
That's why I'm changing it to lowercase, yeah. Okay, so now that we're consistent, how do we set this double integral up? What are we integrating? Yep. And maybe we go dy dx. So then what's the lower bound for y? 0. So we're going from bottom up, right? And what's the upper line or curve? And from left to right, our constants are 0 to 1. In the interest of time, can I just tell you the answer? Okay, so after you do the integration, you're going to get 8/3 for the mass. Once you have the mass, now you can find x bar, and we'll just worry about the setup here. Still going to be the same region, 0 to 2 minus 2x, 0 to 1. The only difference is that our density function, when we're finding x bar, needs what in it? Needs an x, right? So keep in mind this was x, this is density function, if you need to write it down, dy dx. Yep, and then out here we need 1 over mass, right?
Wait, when you put the bar on top, is that your way of writing the center of the
Yes. Otherwise it's just any old x coordinate.
No, because like our teacher, or like Mr. Pierce does a CM, so I just didn't know.
CM,
Yeah, here X and then subscript.
like this.
Yeah.
Yeah, this is how we write it.
Is that like more common notation or just?
In math, yeah.
I feel like this everyone makes.
Everyone has different notation, but it's all the
Can I
same
just
stuff.
make my own notation?
As long as you
That's
define
what
it,
I
yes.
meant.
Everything is just my name.
No, that's what Feynman did. He created his own math notation, and then he was trying to help someone with a math problem, and they were like, "What are you doing?" So he had to go back.
Okay, so 3/8. Does that make sense? What?
As long as you define it.
As long as you define it, you have to tell me what that is. You can't just start throwing random characters on there. Like I used to have students that would do random characters just because they had time. They would draw like vegetables or cartoon characters, like Carl, he used to do that. But he would tell me that that was a symbol or for whatever. Extra credit? Nah. I'll just smile when I grade your test. Which
Can
is
we like say that 2 equals 3 and 1 equals 2?
No.
Just to make things difficult.
No, you can't. By the way, after you set up this integral, you get 3/8. Again, I'm worried more about the setup at this point.
Does the double integral then equal 1?
No, it just ends up like, I mean, it will It's not a thing that always happens.
Okay.
It's a coincidence that it does
For
work
this
that
one.
way. For this one, yeah. When you find the y coordinate, same setup. What's the only difference? Y instead of an x, so it'll be y times 1 plus 3x plus y, dy dx. And again, I'll just tell you the answer. You get 11/16. A good mental check to make sure that you actually know what you're doing and not just blindly following steps. These coordinates should be located where? Somewhere in the lamina, right? So if you get a coordinate that's out of those
Doesn't that
bounds,
happen sometimes?
well, yeah, if you make a mistake.
No, but
Like,
like
in
sometimes
physics.
the center of mass is found outside of the actual shape.
Well,
But
if
Like
the
with the
shape
ring,
has
like
like
the
a
center of mass.
Mm.
yeah, like
Yeah, but if you have a lamina that's, like a full solid object, it's going to be on it. Yeah, I know what you're saying. If you have things missing and stuff like that, that's different.
Wait, so
Yeah.
like if in the real world, like, because you're finding mass, but that's not like in kilograms or anything. That's just like, what do the numbers mean?
What is
I mean, it's like
No,
I'm going to stop here. This was your plan all along, wasn't it?